Hi everyone, welcome back. Today's class is going to be based off of Linda Allen's textbook, section 4.10, and we're going to be going over a linear pharmacokinetics model. So this has a couple of basic properties. Basically the idea is you're taking a drug orally, and then it goes into your stomach and then your gastrointestinal tract for a while, and it passes from your GI tract over to your bloodstream. And what we care about is the rate at which the drug is in your bloodstream, so that determines the efficacy of the drug under certain conditions. So let's write out all those conditions. So we ingest a drug orally, and it passes into the GI tract, into the gastrointestinal tract, tract. So GI tract at some rate d of t. Okay, then once we've done that, the drug passes from the gastrointestinal tract, passes from GI tract to the bloodstream at a rate A proportional to the amount proportional to the GI tract concentration. X of t. And lastly, the drug leaves the blood. So perhaps it's metabolized by the kidney, or perhaps it's taken up by something else. Leaves the blood at rate, let's call it B, proportional. Actually, let me put this in color just so it's more obvious that these are parameters. Let's see, X of t, B, D of t. Proportional to the blood concentration. Blood concentration Y of t. Okay, and so what we have is we have a compartmentalized model. So this is similar to the difference equation models we saw in the first half of class, like the SIR model, except in this case we have just different compartments, one corresponding to the GI tract. So this is the GI tract, and we have some amount X, and we have some other compartment. So this is the blood, and we have some amount Y. And so what comes into the GI tract? Well, we have D of t. So at any time, you have some amount that's passing into the GI tract, and we're going to assume it's some continuous, well, we're not going to assume it's a continuous function. We're going to assume it's some function of time. And we have some amount going from the GI tract to the blood. So this is going to be some amount A times X of t. And then we have some amount that's leaving the blood, which is going to be B times Y of t. And we can write this out as a system of differential equations. So dx dt is going to be equal to, well, minus ax of t, because that's the amount that's leaving, plus d of t, since that's the amount that's coming in. And we also have dy dt, which is equal to, well, you have ax of t coming in, and you have by of t going out. And for the purposes of this analysis, let's assume that both a and b are greater than 0, since they're some proportion. And a is not equal to b. Okay, this just makes some of our analysis a little bit easier in a moment. Because if they're equal, it turns out they have equal eigenvalues, and that makes life complicated sometimes. So we can also write this as in matrix form. So alternatively, we have that x dot, y dot, these are both x dot of t, y dot of t, is equal to some matrix, and this matrix is going to be minus a, 0, a minus b, times x of t, y of t, plus d of t, 0. And we can rewrite this as this is going to be capital X dot of t. This here is going to be the matrix A, this here is just going to be ordinary x of t, not the derivative, and let's call this vector g of t. Well, then, since this is a system of linear system, non-homogeneous system of differential equations, we know the answer to this. So this is x of t is equal to e to the at times x naught plus e, where x naught is just the value at x of 0, times plus e to the at times the integral from 0 to t of e to the minus as g of s ds. Okay, so that's a formula from a previous lecture, and it's also something you can derive. And note that the eigenvalues, values of a, are minus a and minus b, because it's lower triangular, and are negative, because we assume that a and b are positive. So we know that the homogeneous solution, so without inputting any d of t, any drug, the homogeneous solution, which is just, let's call it xh of t, is equal to e to the at times x naught. Well, that goes to 0 as t goes to infinity, because both the eigenvalues are negative. Which sort of makes sense if you think about it intuitively, right? So if you're not, the homogeneous solution is the one where you're not adding drug into your system. And the drug is passing out of your system at some rate. And so eventually, you won't have any drug left in your system if you don't keep on inputting drug into your system. So thus, we know that the limit as t goes to infinity of x of t is equal to, well, we know that's the homogeneous plus the particular solution, but the homogeneous solution goes to 0. So as t goes to infinity, this is just the limit as t goes to infinity of e to the at times the integral from 0 to t e to the as, where we're using s as the variable inside the integration, of minus as, g of s ds. And now all we have to do is solve for e to the at. And so want to solve, what we want is e to the at. So how do we do that? Well, notice that at is equal to minus at 0 at minus bt. And it turns out we can do an eigendecomposition of this, minus a minus b over a, 0, 1, 1. And this is going to be minus at, 0, 0, minus bt. One of the things that is quite important actually is if you were to, let's put this in a different color. Minus at, bt. It turns out that if you remove the t from it, then all you do is the eigendecomposition remains the same, but you have, you don't, instead the eigenvalues are different. So, and this sort of makes sense because you're just multiplying everything by t, which means you're scaling all the eigenvalues by some value t, and you're not actually changing anything else about the matrix structure. A over a minus b, 1. Okay, this happens to be the inverse of minus a minus b over a, 0, 1, 1 inverse. And I'm not going to multiply together, but when you multiply this all out, you'll see that this is actually an eigendecomposition, and you end up getting a diagonal matrix. And thus, from the material we covered in the last lecture, we know that e to the at is equal to, well, all these things multiply together, minus a minus b over a, 0, 1, 1, times the e to the minus at, 0, 0, e to the minus bt, times minus a over a minus b, 0, a over a minus b, 1. And so we need to multiply this together. Let's multiply together the last two matrices first. Minus a minus b over a, 0, 1, 1. Well, when you multiply this out, you're basically just scaling it all. So diagonal matrix multiplied by any matrix, just scaling all the columns. So So this is e to the minus at times minus a, times minus a over a minus b, and e to the minus, scaling all the rows, not all the columns. 0 e to the minus bt times minus a over, let me get this right. Okay, so we have e to the minus at times each of those, yep. And then we have 0, okay, so scaling the other row. A over a minus b, and e to the minus bt. Okay, hopefully I did that multiplication right this time. And you multiply these two matrices together, and this is a little bit harder, but just standard matrix multiplication. Turns out that, luckily, the a minus b over a cancels out with the a over a minus b, because you just get e to the minus at up here in the upper right, 0. And here you get a over a minus b times e to the minus bt minus e to the minus at, and e to the minus bt. Okay, and so now all we have to do is we have e to the at, or e to the as if you replace the t's with s's, and then you just have to plug things in, and you can, in theory, solve this. Yeah. Now, that's a little bit of a pain, because we do have to do a lot of matrix computations. Alternately, you might notice that the very first equation doesn't have a dependence on y, and so there's actually another way you can solve this particular system of equations. So alternately, notice that x dot is equal to minus ax plus plus b of t, and y dot is equal to ax minus by, and this has no dependence on y. So what we can do is can solve for x of t first, and then solve for y of t. So let's go ahead and give an example where we actually give some constant. So we solved it in general using the matrix exponential a little bit ago. Often you will have some parameters, and so you can solve them piece by piece. So let's say that d of t is equal to 1. So we have some constant influx of drug. X of 0 is equal to 0, and y of 0 is equal to 0. So you start out with no drug in your system, and you're constantly inputting it. Well, then you have x dot is equal to minus ax plus 1. Y dot is equal to ax plus by. And so notice that x dot equal to plus ax is equal to 1. This is a first order linear differential equation with constant coefficients. You have several different ways of solving it. You can use an integrating factor, or here we can use the characteristic polynomial. So this, characteristic equation. So this gives you lambda plus a is equal to 0, lambda is equal to minus a, which implies that the homogeneous solution is equal to c times e to the minus at. And so then we also need to get the particular solution. So the particular solution, xp, is going to be equal to, we're going to guess an ansatz that's equal to some k. Well, then we have ak is equal to 1, which implies that k is equal to 1 over a. So xp of t is just equal to 1 over a, and this is also a function of t. And so then you have that x of t is equal to xh of t plus xp of t is equal to 1 over a plus c e to the minus at. Let's see, so this is homogeneous solution, particular solution. And then we also need to solve for the initial value problem. So if we solve for x of 0 is equal to 0, well, that's equal to 1 over a plus c, which implies that c is equal to minus 1 over a, which implies, so this is plugging in initial value problem. So this implies that x of t is equal to 1 over a, 1 minus, 1 minus e to the minus at. And now we have x of t, we can plug it back into b of t. So need to solve for, plug it into y of t. Y dot is equal to ax plus by, which implies that y dot is equal to 1 minus e to the minus at. Since when you multiply out, the 1 over a and the a cancel out, plus by. And this is also a first order, so you end up getting another first order differential equation. So with the same techniques, either a characteristic equation or using an integrating factor. I'm not going to go through the proof of actually solve this in detail, but you end up getting that the y of t is equal to 1 over b plus e to the minus at over a minus b minus a e to the minus bt over b times a minus b. And this allows us to get a couple of limits. So the limit as t goes to infinity of x of t is equal to 1 over a, and the limit as t goes to infinity of y of t is equal to 1 over b. So basically, if you're constantly inputting the drug orally, these are the concentrations that are going to appear in your GI tract or your bloodstream, which is important to know because this determines how much of the drug is flowing around you based on how you're administering the drug, which is important for understanding drug dosages. Now, in reality, you're often not constantly taking the drug at every moment in time. So in reality, often you get something periodic instead. What we care about is a periodic forcing term. And periodic, e.g., if drug taken every 6 hours, and released at a constant rate into GI tract over half an hour. So if we did that, then we'd have some function d of t is equal to 2 for 0 less than or equal to t less than or equal to 1/2, and 0 for the remainder of the 6 hours. I guess I need that to be less than t less than 6. And d of t plus 6 is equal to d of t. That should be a 6, not a t. d plus 6 is equal to d of t. So we have a periodic forcing term, basically. And one of the things that you'd want to do if you were trying to understand how to design a drug is you'd want to also create a dosing schedule such that the concentration in your bloodstream, y of t, was within some parameter range for the drug to be most effective. And so this is one of the ways you can use differential equation systems to understand pharmacokinetics. And we'll be seeing more of these sorts of things in the next section as we get into more nonlinear examples. So for this linear example, it's really easy to explicitly compute everything. For the nonlinear ones, things get a little bit more difficult. And I think I will end the lecture here. So, there will be some problems in your breakout session on the problem set. Talking about the pharmacokinetics models and understanding, playing with it in a little bit more detail. So thank you very much, and I'll see you in class.